Okay, to my past few videos here, we've been looking at long division and also synthetic division. In this video, we're going to focus on a couple of really important theorems here. We'll call these the remainder theorem as well as the factor theorem. So the remainder theorem, let's go ahead and take a look at it first. We say that if the polynomial f of x is divided by this x minus c thing, and as a matter of fact, I want to point this out, if it's in the form x minus c, we'll be able to use synthetic division. But we say then the remainder is f of c. So essentially what we're going to see here is this, no pun intended, when we divide some polynomial f of x in here, and we put some c value on the outside, we say c, okay, I'll not write x equals c, I'll just write c, then what you're going to get is this thing where we'll drop down the leading term here, and then we'll multiply and then add and multiply and then add and multiply and then add. But the idea is that this last number that you see right here, which is the remainder is actually equal to f of c. So the nice thing about this remainder is that it's not just the remainder, it's actually the y value you get when you plug this into the function. So what that's going to allow us to do is things like on checkpoint 5 here, we say given some function, this third degree polynomial, it says use the remainder theorem to find f of -4. So what I want everybody to see here is this. If I were doing this the quote-unquote old-fashioned way, I would have to actually take out all of my x's here, and I would have to go plug in the input that we're finding for, which in this case is -4. So -4, -4, -4, and then evaluate this. What I want you to see is that if we're using the remainder theorem, then all this says is we just need to drop in our f of x in here, its coefficients, and then we'll drop in the c value, or the value at which we're evaluating out here. And then we'll carry this out. So we say -4 times a +3 is -12. -12 plus a +4 is -8. -4 times a -8 is a +32. -5 plus a +32 is a 27. And we say 4 times 27, positive times a negative, is a negative here. And we get 80 plus another 28 is 108. So we say -105 if I've done my mental math correctly here. So we're going to put a little note here. We're going to say that this is equal to f of -4. In other words, this is our y value that we get when we plug that into the function. So we could say, making a table of values here, x and f, we could say when we plugged in -4, then our output was -105. And also that it's the remainder of this function right here when we divide by x plus 4. So now when we look at the factor theorem, I love the factor theorem just for one sheer fact. It says let f of x be a polynomial. Then we say that f of c is equal to 0 if and only if basically x minus c is a factor of f of x. So I want you to consider something here. If f of x has a bunch of factors and one of them is x minus c, then when we set this equal to 0 to solve this x minus c, I'm going to add c to both sides here. And what I find out is that x is equal to c if and only if this is a factor. But if that is a factor, then what we're saying is that this right here equals 0 when we multiply all these factors together. In other words, when you plug c back in for x, you'd get c minus c, which gives us 0. So basically, if x minus c is a factor, is what this says, then x equals c is at 0. And if x equals c is the solution, then x minus that solution must be the factor. So again, if f of c equals 0, then x minus c is a factor. But if x minus c is a factor, then f of c is 0. So this says, let's solve the equation here, where we have this cubic set equal to 0, given that -1 is a 0 of f of x. So here's what we want to start with. We say solutions. Another name for a solution is a 0. Another name for that is an x-intercept. But what we've been told already is that one of the zeros of this function right here is -1. So what I know is this. If this is a 0, then x plus 1 is a factor. So because x plus 1 is a factor, what we're going to do is we're going to take the original f of x here, which had 15x's cubed, 14x's squared, -3x's to the first, and -2 constants, and we're going to divide it by this value right here, this factor. And so when we divide it, remember I'm actually going to put a -1 out here. That'd be this value right here, that is the 0. But we're going to go ahead and divide this out. So I get 15 here. -1 times 15 would be a -15. -15 plus a +14 is a -1. -1 times itself is a +1. -3 plus a +1 is a -2. And the -1 times the -2 is a +2. So we get 0. So something we anticipated happening. A couple of things. We could say, one, f of -1 is 0. Also that our remainder is 0. So that this must be a factor of the original. And then last but not least, we say that this quotient here, 15x squared minus x minus 2, what we can say is that the original f of x is equal to now x plus 1 times this leftover quotient, 15x squared minus x minus 2. And that's just saying that basically the divisor that you divided by times the quotient that you got left over is equal to the original f of x that you started with. So now if I want to solve this, I'm going to solve this by factoring, but that just means that I have to continue to factor this right here if it's factorable. So I'm going to try to factor this right here. Let's see. Let's try 5x and 3x, and then we'll do a plus 2 and a minus 1. So checking my outer and my inner here, it looks like we get negative 5x and a positive 6x. You know what I'm going to do? So I'm going to make this a minus 2 and a plus 1. So checking my outer and my inner here, I notice that I get 5x minus 6x, which is negative x, which is what I need here in the middle. So we say that because these are my factors, we used one of the zeros to say we know one of the factors. And using that, we were able to find the other two factors by dividing first and saying that this leftover factors into our other here. So if we set this equal to 0 now and solve this, then we're going to get either x plus 1 equals 0 or 5x minus 2 equals 0 or 3x plus 1 is 0. So solving these, here we get x is negative 1. And that's one of the zeros we already had up here. I'm going to write solutions, zeros, x-intercept. Since I put a box around it over here, sorry, I kind of polluted the water there. We say negative 1. And if I were to solve now, 3x plus 1 equals 0, I'd get 3x equals negative 1. And dividing by 3, we get x is negative a third. And our last 0 is going to come by solving this 5x minus 2. If we add 2 and divide by 5, we're going to get 2/5. So these must be the zeros of the function. We were able to find those just by knowing one of the zeros and then dividing it out and then factoring what was left over. Cheers.